Like one or two of them, because log differentiation is a great technique that works in pretty much every situation. And again, I only say pretty much because I can't think of any case where it doesn't work. All right, but I don't want to put myself on the hook for saying it works all the time. All right, so we have f of x equals x squared. You know the derivative of that is 2x, but let's see how that would look using log differentiation. So first I'm going to write it as y equals x squared. All right, then I'm going to take the natural log of both sides of the equation. All right, the purpose behind using log differentiation is so that you could use log rules to simplify a situation. All right, that's the whole idea. So when you see a product within a function or a quotient or a power, log differentiation could be a technique that you want to use. All right. Now, if that's a numerical power, then it's a power function most likely, in which case you probably don't want to use logs. Generally, you want to use it for a variable power. But we have those three rules for logs, and they do help. So let them help. So I have the natural log of y equals 2 times the natural log of x. If I differentiate both sides, I get 1 over y dy dx equals 2 over x. All right. Next step in the process would be to get dy dx alone. That's the objective here, to find the derivative. 2 over x times y. If possible, we want to convert from being in terms of y to a function that is solely in terms of x. All right, so I swap out the y for an equivalent expression in terms of x. And since y is the same thing as x squared, I can make that substitution and get a result of 2x. All right. I mean, it's overkill. It's the equivalent of killing a fly with a sledgehammer, but yeah, it gets the job done for this problem. It's an effective solution. Not as elegant, I guess, as the power rule, which is one step and done, but at least to get started on something that's very familiar, it's hopefully going to sell at least the benefit of knowing something like this. All right, so we know it works. Now let's apply it in a more challenging situation. So in number 2, we have something that would be quotient rule, or if we move up the radical, it would be chain rule. But if we do it with log differentiation, maybe it'll be easier. Maybe it won't. But it's the maybe that allows for hope. You do enough of these, you start getting into a habit of leaving a little gap after the equal sign, because you know you're about to chuck a log in there anyway. Or you just write it in terms of log, right? Of the log right from the get-go. All right. So the first question involved the natural log on the right-hand side with a power. Here, there's no power, or at least no obvious one just yet. But there is a quotient. Right? So I could write this as ln of 1 minus ln of this radical, but I'm not going to write it as a radical. I'm going to write it as x squared plus 1 to the 1/2 power. All right, natural log of 1 goes to 0. All right, so I'd be looking at negative 1/2, because this is a power rule case. Negative 1/2 ln of x squared plus 1. And that would be equal to ln of y. All right, so we've cleaned it up. Now we could use differentiation techniques to get our derivative. So in this case, both sides would involve a natural log. Right? I suppose the only way that you could avoid having to take the derivative involving natural log is if there was an e or some kind of exponential in there somewhere on the right-hand side, perhaps. That would cancel with the natural log. I mean, that would be a great situation. On the left-hand side, it's your 1 over y dy dx. On the right-hand side, you have a constant multiple of 1/2. And then we just need the derivative of the natural log of x squared plus 1, which is what? Say it again? That's part of it, times 2x, so we'll just put the 2x up top. All right. Well, if you're using a technique called log differentiation, it's sort of a requirement that you know how to take the derivative of a natural log, right? So this is a good, simple relation. Right? 1 over u times du dx is fine, but this is a little bit simpler. So the derivative of what is within the logarithm on the top, and whatever is within the logarithm goes right on the bottom. And then if you have you know, a base other than e, then you have to correct for that. But not the case here, so we don't worry about it. All right, so we can clean it up if we want. We can kill the 2's, attach the negative there. I do have to multiply both sides by y. Depending on the requirements for simplifying, it could just be a matter of taking what I have on the right-hand side in its current form and just multiplying it by the equivalent y relation and call that our answer. Right? The reason we would be allowed to do that is because if a question didn't say to simplify and it's not a multiple choice question, then you leave it in any form you want as long as it's equivalent to the correct answer. All right? But you know, I just can't stop myself sometimes. So the right-hand side simplifies down to negative x times x squared plus 1. And then I have to multiply it by the y, which is 1 over the square root of x squared plus 1. So I'd get a final answer, if I were to clean this up fully, negative x over x squared plus 1 to what power? 3/2. Very good. Yeah, because this is a power of 1, power of 1/2, keep the base at the exponents. Okay. And so that would be my derivative. Now, you could look at it and say, yeah, I could have got that quicker with the chain rule, quotient rule, whatever method you like. Again, that's not the point, right? Because I say, yeah, totally, I agree with you. I'll do you one better. I could have done number 1 way easier than this one, you know, like than this technique. That's not the point. It's the point is to learn how to do it this way, so that when you come across a beastly looking problem, you have this as a technique that's available to you. So number 3 is along the same lines. It's not made up of anything too crispy. But then you get to number 4, and where numbers 1, 2, and 3 are problems that you have the luxury of choice, number 4, you don't have that luxury anymore because you're not going to be able to do it using another technique. Right? So there's not a case where, I mean, there's cases you can learn in Calc 2 and Calc 3, but there's not a case associated with product rule, quotient rule, chain rule that's going to get you this derivative without using log differentiation. All right? So y equals x to the x. Natural log both sides. It allows for that exponent to become a coefficient. ln y equals x ln x. Differentiate. Okay, so a little familiarity is a good thing here because we now know that the left-hand side is just always going to be 1 over y times dy dx. Assuming you're starting off with a y equals, the left-hand side is just going to be that. Now, if it's some implicitly defined function, you know, like xy equals x to the x, something like that, it might change. But if it's just y equals, you can rely on that. A little less thinking involved. Product rule. I have two factors. The first times the derivative of the second, what's that going to give me? A 1, all right, because it's x times 1 over x. Plus my second times the derivative of the first, which is going to give me what? ln of x times the 1. All right. Then multiply both sides by the y, which is x to the x. And you come up with your answer of dy dx equals 1 plus ln of x times x to the x.